at this point, we have a pretty good understanding of the major influence of temperature on viscoelastic material behavior. That understanding has been based on experimental observations that I tried to summarize through the plots that I've drawn. Now what we'd like to do is we'd like to go ahead and actually quantify those observations or embody them within a model. So we'd like to model temperature effects. And there are a number of key observations that we've already stated which is going to guide that model. So now first of all, what we've observed is that the viscosity is a function of the temperature, and so is therefore the relaxation time. The elastic moduli that appear in our model, such as E and E infinity, if the polymer is well modeled by the SLS approach to the standard linear solid model, then those are the only two parameters, elastic properties, that appear, E and E infinity. We've said that those are approximated as being not dependent strongly on temperature. The eta, the viscosity, and the relaxation time, therefore, are much more strongly dependent on temperature changes. So now eta is not equal to tau, of course. I have to scale by E. But instead of scaling by E, I'm going to make this an inequality by scaling the left-hand side by the value of the viscosity at a reference temperature. And let's pick that temperature, why not, to be the glass transition temperature. And the one on the right, the relaxation time, likewise by the value at glass transition temperature. And so you see the equality holds if I divide by E the left hand side, and the equality holds if I divide by E the left hand side, and therefore the equality holds when I take the ratio of those two sets. So that's essentially the idea. Now in this picture I'm going to call, by the way, eta of Tg, let's call that eta G, okay, and tau of Tg, we can call that to be tau G, the value of the relaxation time at the glass transition temperature. If Tg is a material property, then tau G also is. So now these are functions of time. It's the same function. Let's call that function A of t. So that's the ratio of either the left or the right hand side. Let's think in terms of time. I like time when we talk about relaxation, because it's the characteristic response time of the polymer, relaxation time. So let's stick to time and let's focus on that picture. So now I don't know what that function is, but I could characterize it. But what I'm characterizing, remember, is the influence of temperature on time. It is time, relaxation time, that I am monitoring. Now let me make a very vague discussion. What we've observed in the previous slide is that the way I have variations in time of the relaxation function is the same pictorially the way in which I have that relaxation function change with respect to temperature. So the two pictures are the same. It's just that in one case I have time, in one case I have temperature. This is called the time-temperature equivalence principle. Time, temperature equivalence. Okay, and the time-temperature equivalence principle guides eventually the major, let me say, input that we're going to make into our model. Now, but that picture, the equivalence in the two pictures, has a fundamental point to be careful about. One scale is log, the other is not. So in other words, time appears through a log, temperature variations appears without a log. Okay, so that's as much as I am going to go in the discussion of what I'm about to state. So that motivates us that whenever I'm working with time, I should be working not directly with it, but rather through its log. So I'm going to take its log. Importantly, I'm taking its log with respect to the 10 basis, so it's not natural logarithm. And if I do that, I will get, of course, log of tau minus the log of the glass transition relaxation time. Okay, so now what we're saying is that variations in temperature go through a log, but the variation of the temperature goes as it is. And now I'm gonna write on the left the log of A. That's gonna reflect variations of time on a log 10 basis. And on the right, I'm gonna write directly a function of time. And that function has to be motivated by experimental input. And experimental input has revealed that a function of the following form is surprisingly accurate. This is called the WLF equation. It's a model to relate how the relaxation time depends on the temperature based on the time-temperature equivalence observation that we've stated. And WLF stands for Williams-Lendl theory. Now here we have some constants. C1 is something without units, 17.4, and C2 is 51.6. You can say kelvins or degrees Celsius, depending on how you'd like to measure the temperature change. Either way, it is equivalent. And these constants are said to be universal. Now, universal in the sense that when you look in this equation, you don't see a material property appearing. So you don't see you do see a material property, namely Tg and these constants, but it turns out that apart from Tg, these constants do not really depend on the type of polymer you are looking at. In other words, this log A function is going to depend on the type of polymer you're looking at only through, surprisingly, through the glass transition temperature of the polymer. So, and in that sense, it is universal. So it is valid for a wide range of polymers. Let me note that that wide range is mostly amorphous polymers. So you're going to learn more about different types of polymers. They're crystalline polymers, semicrystalline, amorphous. Amorphous meaning that the polymer microstructure has no distinct, well-observed order. Polymers typically are described as a bowl of spaghetti in order to explain their elastic, viscoelastic, etc., different types of material behaviors, mechanical responses. And amorphous is going to be essentially a picture that reflects that bowl of spaghetti, where the spaghetti strands are replaced with polymer chains, essentially. Now, and so this universal nature applies mostly to amorphous polymers, and in a specific temperature change, in particular when the temperature is lying in that range. Okay, so let us keep that in mind as much as we can. Okay, so that is the way one incorporates temperature effects into an explicit model. So next, what we would like to do is we would like to just quickly go ahead and finally, now that we have a model for temperature effects, we'd like to demonstrate that through a simple example.